Good morning all. In this video, I'm going to discuss about operational amplifier DC characteristic, that is input bias current. As I've already discussed in the previous video, the non-ideal DC characteristic that is going to add error or offset voltage to the DC output voltage are input bias current, input offset voltage and thermal drift. In this video, I'm going to discuss about input offset current. So what is the input offset current? The input offset current is nothing but a small difference between the IB plus and IB minus current is called as the offset current. As you already seen in the previous video, that is in presence of input bias current, what will be the output voltage? So bias current compensation will take the condition that both the current will be equal to both the current entering into the terminals of the op-amp is going to be equal, but due to transistor mismatch, practical case, the op-amp bias currents are not going to be the same. So this IB current is not equal to IB minus current for the case of the offset current. So there is small difference between these two currents we normally call as the input offset current. That is IOS is equal to IB plus minus IB minus. So in this video, we are going to see in presence of input offset current in the circuit, what is the error voltage we are going to get at the output and what is the compensation technique we can use it. So for the BJT op-amp, this IOS can take the value 200 nanoamps, and for the FET operational amplifier, this input offset current can take the value of 10 picoamps. Now let us see the analysis part of input offset current. The left side, the circuit diagram shows the inverting amplifier with the bias current compensation. So here already we are included our compensation in the circuit in order to compensate for the input bias current. And now in presence of input offset current, what will be the cause of the what will be the output you are going to get it. Okay, first we'll start the analysis part. From the circuit diagram, first we are going to find what is the voltage V1. See, this diagram is familiar for the previous analysis. The same diagram we are taking here. So the voltage across our compensation is given by V1. So V1 can be written as IB plus into our compensation. Let us consider that is equation number 1. And next one is that, as we already know, the difference between these two voltages is given by VD, differential voltage. For the ideal case, this VD is considered to be 0. Since your VD is 0, whatever the voltage that is present at the non-inverting node, the same voltage will be present in the opposite inverting node. So the voltage now present in the non-inverting node is minus V1. So the voltage that is present in this node A is also considered to be V1. So from this I1, we can write I1 is equal to V by R formula, that is V1 divided by R1, and we are going to consider that is equation number 2. And now the next step, we are going to substitute the equation 1 in 2. So we are going to substitute equation 1 in 2. That is, in the place of V1, I'm going to substitute the equation 1. So your I1 will be equal to IB plus or compensation divided by R1. Let us consider that is equation number 3. And next one, we are going to apply KCL at node A. Okay, what is the Kirchhoff's current law? Let us see what are the current that is entering this node and what are the current leaving this node. See, if we see here, the current that entered this node are I1 current, and see the arrow mark, the I2 current entered this node, and the current leaving this node is given by IB minus. So the sum of the current entering the node will be equal to current leaving the node. So we can write the equation as I2, that is IB plus I1 plus I2 will be equal to IB minus. These two current will be equal to IB minus, or from that I2 can be written as IB minus minus I1. So IB minus minus, what is I1? From the equation 3, I1 we already know, IB plus R compensation. Substitute equation 3 in the place of I1 here. So that will give the equation number 4. So from this equation 1 we got what is the V1 value, and the equation 4 we got what is the I2 value. Next, from the circuit we are going to apply KVL. That is, we already know that V0 will be equal to V2 minus V1. This is the equation we already derived for the previous input bias current. So now V2. What is V2? V2 is nothing but I2 into RF minus V1. And what is the I2 into RF? I2 from the equation previously from the equation 4, we got I2 is equal to IB minus IB plus into or compensated by R1 into RF minus V1 from the equation number 1 we got as IB plus into or compensation. So from this we are going to take this IB minus into RF minus from this two equation I'm going to take IB plus into or compensation commonly outside. So what I'll get is R1 RF plus 1 divided by R1. Okay, 1 plus RF by R1 I'll get. If I substitute that one, I'll get R1 plus RF by R1. Next, I'm going to replace the OR compensation. We already know that OR compensation is given by R1 parallel with R2. Okay, R1 parallel to R2 is given by OR compensation, which we got from the input bias current analysis part. So in the place of OR compensation, I'm going to substitute as R1 RF divided by R1 plus RF into R1 plus RF by R1. Here, this R1 will get cancelled. R1 plus R1 plus RF will get cancelled. So what is the remaining term I'm getting is V0 is equal to IB minus RF minus IB plus here one RF is present. So IB minus RF minus IB plus into RF. From this I've taken RF commonly outside. So I'm getting the equation as IB minus IB plus. Okay. What is IB minus IB plus? We know that the difference between these two base currents, we normally called as the input offset current. So V0 will be equal to RF into input offset current IOS. So this is the conclusion we are making, that in presence of the input offset current in the circuit, your output will be depending upon the input offset current. Now let us see this with an example. So we already know that as a manufacturers have already has been mentioned in the subscription sheet that for BJT operational amplifier, the IOS specification sheet as IOS is equal to 200 nanoamps. So now let us take the example. We are considering an inverting amplifier with Vi 0 and we are taking the feedback resistor of 100 kilo ohms. From the previous equation, it is clear that V0 is going to depend on the input offset current, that is IOS into RF. RF is 100 kilo ohms. What is the IOS value we are taking here is 200 nanoamps. So we are getting the error voltage of 0.02. So in presence of the input offset current in the circuit, for the feedback resistor value of 100 kilo ohms, for the input of 0 volt, we are getting some amount of error voltage or offset voltage of 0.02 voltage. Okay, how we can compensate for the presence of this input offset current? That is the next thing we are going to see it. From the equation 5, it is clear that the effect of output current can be minimized because since your V0 is equal to RF into IOS, if I reduce the value of RF, I can reduce the error in the output voltage. But if I reduce the feedback resistor, what will be the case is that the overall gain of the circuit will get affected, operational amplifier circuit. So we cannot reduce the RF value. So what is the alternate methods they can use in order to compensate for this input offset current? So a T feedback network is used to minimize the effect of offset current. If you look at the circuit diagram, here the feedback resistor is being replaced by this T feedback network, and this T feedback network is going to produce a solution for this input bias current because this T feedback network is going to provide a resistance, that is it is going to keep the resistance feedback resistance. At the same time, it is going to keep the resistance to ground to a low level. So this is going to act as a solution for the input out. In order to reduce the effect of the input offset current in the circuit, we are going to use this T feedback network in the circuit diagram. Okay, the reference book used for this is a linear integrated circuit by Rai Chaudhary and Shelby Jain. Okay, all in this video discussed about and the other non-ideal DC characteristic which has been added error to the output voltage in presence of zero input condition, that is input offset current, and what is the effect we'll be getting in presence of input offset current in the circuit and how we can compensate for that. Okay, thank you all. Next video, I'll discuss about what is the input offset voltage and thermal drift. Thank you.